Okay, all right. Okay, thanks. Thank the organizer for letting me speak. So this series of works is done together with Xue Yang and Ashwin, who's here, and my colleague Ying Chen at Perimeter. So what we really want to understand better is the subject of quantum magnetism. It's an intrinsically hard problem because the system is strongly coupled. There's no obvious provision theory to do, and the Hamiltonian typically looks something like this. So okay, by the way, in this talk I'll be focusing on two-dimensional quantum magnetism. So it's a lattice system where we have some spin half moments sitting on each side. And the Hamiltonian typically looks like Heisenberg plus dot dot dot. Usually the dot 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 may be more interesting than Heisenberg, but it's not obvious how you solve it. Right? The ancient approach, which has been successful in many occasions, is to just do a naive mean field type of approximation. You imagine that the spin is ordered in some way. You replace one of the spin by this expectation. It becomes a single body problem, and you solve it self-consistently. So the problem with this approach is that the kind of state you get is almost guaranteed to not be highly entangled. Right? So nowadays, when we want to understand more exotic or highly entangled phases, we need to do something better than that. So one trick that has been fruitful is called Parton trick. So I start by rewriting my spin operator as a composition or a bilinear of a fictitious fermion operator I call spin-on. So this alpha, beta are spin indices. And then I can think about a mean field, not in terms of the bare spin, but in terms of the parton, the fermion parton. That essentially converts the problem to a free fermion problem, which everybody knows how to solve. And then I can introduce fluctuations on top of this mean field. But here, the slightly funny thing is the fluctuation, once you introduce the fluctuation, is guaranteed to be a gauge theory, or a lattice gauge theory. You can see from here that in this decomposition, if I multiply one of the these fermions by a complex phase factor, nothing changes. Absolutely nothing changes. So that's the gauge redundancy intrinsic here. And practically, there are many different gauge groups one can choose depending on context. U1, Z2, SU2. But for this talk, I'll be focusing on U1. There are some motivation for that. Okay. But the bottom line is what this trick really does is to map the spin system, which is hard to solve, to a system of U1 lattice gauge theory plus fermions. Right? It's hard to solve again, but there are at least some sensible approximation we know how to make. So this Parton approach has been extremely useful historically for accessing highly entangled, especially gapless quantum phases. Right? Essentially, now the idea is I have some fermions that couples to a U1 gauge field, so I can let the fermions do crazy things. Crazy but controlled things like being gapless. Right? They can form a Fermi surface, they can form some gapless Dirac fermions, and then at the end of the day, they couple to a U1 gauge field. So those from the underlying spin system point of view will be extremely interesting phases. So one prominent example, which will be important later in this talk, is called the U1 Dirac spin liquid. That's a case where the spin-on fermions form gapless Dirac fermions. Okay, so one of the unsolved questions in this approach for quite some time is that, okay, I can access these funny phases, but it's not completely clear how to access more conventional, like ordinary symmetry breaking kind of phases, some magnetic order. Right? It would have been much easier if these particles are bosons, right? That's known as Stringer boson, in which case you want to access some magnetic order, you just condense the boson. Right? And by condensing the boson, you also Higgs the U1 gauge symmetry, and then the things become easy. For fermions, it's you have to do a little bit more complicated stuff. Okay, and of course you can say, okay, it's conventional symmetry breaking order. Why do we need such a fancy, such a funny formalism to understand that? Well, the thing is, this exotic gapless phases often feature as competition between different type of symmetry breaking orders. So if you really want to understand this type of phases well, you better understand the actual symmetry breaking phases. Okay? And it turns out there's a reason why this question wasn't completely understood back in the 90s, because that's before the era of topological insulator. It turns out the answer lies in the story of SPT, or symmetry protected topological phases, and that's the story I want to tell you today. Okay? So let me just tell you by an example. It may look funny on first sight, but it turns out to be relevant later. So let me give you an example on triangle lattice. So the details of the band structure doesn't really matter. I mean, okay, it's important, but you don't have to remember it. I'm just showing you that it exists. So I take a triangle lattice. I have a spin-half fermion hopping on it. I have one fermion on average per site, so that's half filled. So I have a staggered pi flux pattern on this triangle lattice, meaning there's a pi flux in the every downward triangle and no flux on the upper triangle. And then I add some spin orbit coupling. Eventually what I get is something known as a quantum spin Hall insulator. Okay, you don't have to remember all this. It's a quantum spin Hall insulator. So the zeroth order information is that it's an insulator. So if I go to low energy, I can more or less forget about the fermions, they're gapped. And then I'm left with a pure U1 gauge theory. It's essentially a photon theory in IR. But it's known that a photon theory in 2+1 dimension is basically just a non-exotic symmetry breaking order. Right? So the photon, you can think of them as the boson out of a symmetry breaking order. And the order parameter that correspond to the symmetry breaking order is known as the monopole operator. So you can think of them as it as an operator that inserts a 2 pi flux into in your space. Okay. Well, now okay. So it's a symmetry breaking order, but what symmetry does it break? Right. Well, as I said, the order parameter is the monopole. So that question is the same as asking what symmetry quantum number does the monopole carry? Right. So, as I said, that insulator is called a quantum spin Hall insulator. That name comes with a meaning.
Sorry. So the previous slide, the upper picture is the gap state. The lower one is gapless.
Okay, so just with this, it's gapless. It has gapless Dirac fermion, but then you add spin orbit, which I was too lazy to draw. That becomes a gapped quantum spin Hall insulator. Yeah.
And the one below.
The one below.
One photon series.
So it's 3D or 2D?
2+1. Yeah. So it's a photon theory.
And that's gapless.
That may or may not be gapless, depending on whether you have a monopole provision turned on explicitly. That will, in turn, again, depend on exactly what symmetry the monopole carries. In this particular case, it turns out it's gapless. It's a Goldstone thing. Yeah. But it's gapless in the Goldstone sense, so there's nothing weird about it. Yeah, okay, so let me continue. So it's a quantum spin Hall insulator. You can write down a response like this, where AC couples to the gauge charge, and AS couples to is conserved as Z spin. But by definition, what that means is if I have a monopole, it carries a spin SZ quantum number as equal to 1. Okay? So morally, that says the monopole operator behaves like something like SX plus ISY. Okay? So in the language of magnetism, that's a non-collinear magnetic order. So if an object like this condenses, I completely break my spin SO3 rotation symmetry. Okay. All right, so that's for spin. Well, it turns out it's also known that if I have a spin half system with spin orbit coupling that gives me a quantum spin Hall, with the spin Hall conductance being 1, that's automatically, in 2 dimension, that's automatically also a Kane-Malay type of strong topological insulator protected by time reversal symmetry. And there are many ways to characterize or define what a Kane-Malay topological insulator is, but this is one of my favorite ways. So the with a K-Malay TI, what happens is that the monopole becomes odd under a time reversal transform. Okay, the monopole goes to anti-monopole, but the funny thing is there's an actual minus sign here if I have a TI background, which turns out also means that if this monopole condenses, which happens in the photon phase, I spontaneously break time reversal symmetry, okay? Even though my band structure has the full time reversal symmetry. Okay? So these two facts are known before. Right? For internal symmetry, it's basically understood because we understood the internal symmetry SPT pretty well. Now the next question is, what about lattice symmetry? The thing is, on a triangle lattice, when you see an order parameter that looks like Sx plus Isy that breaks time reversal, already the most familiar picture would be something like this. That's the most famous antiferromagnet on triangle lattice. But the question is it really that, right? The spin rotation and time reversal property fits, but this picture also comes with a specific pattern of lattice symmetry breaking. So does it fit there? Yeah, so that's the story. Now, I want to figure out how the monopole transforms under lattice symmetries. Let's pick a simple one, a C3 rotation, some 120 degree rotation. Okay? So the answer is going to be discrete, right? So C3, the monopole either is going to be trivial or it's going to pick up a phase of e to the I 2 pi over 3 or something like that. Right? So since the answer is discrete, it doesn't hurt if I try to deform my band a little bit. And the answer is not going to change. So let me deform my quantum spin Hall insulator to something as simple as possible. So as you learned from Jen's talk, there's nothing simpler than an atomic limit. So let's try to do that. The tiny catch is that for TI, you can't literally do that. That's the definition of TI almost. But since to figure out the property under lattice symmetries, the fact that I have time reversal and spin rotation doesn't matter. So let's break all that. Once I break all those internal symmetries, there's no obstacle for me to do this deformation. Okay, so let's deform that, and there is a way to systematically figure out what the atomic limit would look like, as you learned from Jen's talk. And let me postpone exactly how you get that later, but just tell you the result. For the specific kind of band structure I mentioned, the result would look like a picture like this. Basically, you end up with, remember I have one particle per site, so that's like one particle per unit cell. So you end up with one particle per site plus one particle for every upward triangle. And then there's a negative one particle on every downward triangle. The negative particle comes from the notion of fragile topology, which I can explain later in 2 slides, but just bear with me. So effectively, there's a negative charge here. Right. So it turns out that's enough for me to figure out everything about monopole property under lattice symmetry. So if I want to figure out C3, let's say, suppose I want to figure out the C3 property of the monopole around an upward triangle center. So it sees a charge of 1. What happens is that if I go for a full circle, take the monopole is a 2 pi flux. So if I take the 2 pi flux around a full circle, I pick up a full 2 pi flux. So that means every rotation comes with a 2 pi over 3 phase. Right? Essentially, I get an angular momentum that's E times m, the electric charge or the gauge charge sitting at the rotation center times the monopole strength. Okay? And likewise, for the downward triangle center, if I try to do a C3 rotation around this one, because it's a negative charge, I get a minus 2 pi over 3 phase factor when I rotate the monopole around. Okay? So that way I figure out how the monopole transform under the C3 rotation symmetry. And then it turns out once I figure out the rotation symmetry, translation comes automatically. It comes for free. It's because I can think of a translation as a composition of 2 inverse C3 rotations, but around different centers. Right? If I do a C3 rotation around the downward triangle center and then the inverse, like a minus 120 rotation around an upward triangle center, I get, I basically get a translation. And then I read off the phase from here. That's some 2 pi over 3 phase factor when I do translation. Now you take this data. It turns out you stare at this data long enough, you realize that that's exactly what you get with this 120 magnetic order on the triangle lattice. For example, you do a translation, the whole pattern rotates by an angle of 2 pi over 3. Okay. So some of this are also discussed in Shan, Ashwin, and Islam, which yeah. And another funny feature is that, okay, so here I obtained the translation symmetry property by composing different rotations, right? But translation is certainly well defined on its own. So in principle, I don't have to do that. But if you stare at this picture long enough, right, as I said, you get translation by doing opposite rotation on different sides. But then the rotation number is given by the charges on that side. So translation is given by the difference between the charges on different sides. If you repeat that sentence long enough, you realize that's just dipole moment, right? So, and of course, dipole moment within per unit cell is just a long way to say polarization. It's a concept you learned in high school. It turns out that the monopole momentum is given basically by the polarization. It's proportional and perpendicular to the polarization of the underlying insulator. And this, there's a very simple, almost high school level, semi-classical intuition for that. Because if I have a dipole and dipole moment, and I put in a magnetic field, there's a momentum that that's going to be induced on that dipole moment. Right? It's a high school exercise, and that it turns out that intuition is correct even at the quantum level. Okay. So actually, the nice thing is, we can even use this to practically define or calculate, depending on your taste, the polarization for an insulator. Turns out polarization, if you do it in the quantum world, it's a slightly subtle concept, but this gives you actually pretty good handle on that. And also, let me very briefly comment what I mean by negative charges in that picture. As I said, there's a negative charge, what I mean by that. So that's the, by now, reasonably well-known concept of fragile topology. So the idea is, I lied a little bit when I say I can deform my insulator to an atomic limit, even after breaking all the internal symmetries. That's because the insulator itself, turns out you cannot deform that to an atomic limit. But if you supplement with another atomic insulator that has one particle sitting on every downward triangle center, it turns out the whole thing is now deformable to a simple atomic limit, which has one particle per side and one particle per upward triangle center. So that's the notion of fragile topology. There's a calculational recipe for that. Essentially, okay, it's what Jin told you. You go to some high symmetry point in the Brillouin zone, look at the eigenvalues, and try to match them up. Okay, so it's calculable. That's what that's all I need to say. Okay, so now you get something that looks like a duality dictionary. I'm not sure if I really want to call it a duality, but I have a dictionary, so maybe I have a duality. So the notion is, if I start with some free fermion band topology, free fermion band with some topological signature, now I couple it to a U1 gauge field, and essentially view the fermions as my slave fermions or partons or spinons. That becomes some symmetry breaking order in a quantum magnetic system. Okay? And the detailed correspondence is that if I have a spin Hall conductance, I end up with a magnetic order. If I have a King-Malay type of strong TI, I end up with time reversal symmetry breaking. If I have some funny distribution of these charges within the unit cell, you can call these things charge center or Wannier center in some cases, then the corresponding state will actually break lattice rotation symmetry. And if my insulator has a non-trivial polarization, that gives me a translation symmetry breaking with the wave vector proportional and perpendicular to the polarization.
Excuse me.
Yes?
This is a duality at the UV lattice scale.
you can say that. The thing is, if you really want this to hold, you want the photons to couple weakly. So then the lattice UV IR doesn't matter. Right. Yeah. The thing is, these are duality for gap phase, so they are pretty controlled. Right. Once I go to the gap phase, that's another kind of form, which I will go to eventually later. Sure. Okay. Nice. I have a dictionary, but what's useful about it? All right. After all, what I've done in the past, I don't know, 20 minutes is describe to you some extremely detour way to understand conventional symmetry breaking orders. Okay. There are two things that I can think of. One is a little bit pedantic. That's there are some symmetry breaking phases that there's nothing really weird about the symmetry breaking. There's no topological order. There's no funny CFT behind. But if you really want to write down the wave function on some Hilbert space, it turns out to be a bit tricky. You can't have a product state representation of the wave function. It turns out some of those weird or quantum symmetry breaking orders are quite easily accessible in this Parton language. They just have to choose the right fermion band topology. Okay, that's a bit pedantic. The other thing that's much more relevant is that I can now actually access the theory of competing symmetry breaking orders via the theory of competing band topology. And the theory of competing band topology is way much simpler. Right? Yeah, it's way simpler, right? Because we know a great deal about them. Let's say if I want to go from one band topology to a very different band topology, what do? Well, we know that. We close the fermion band gap and try to reopen it in some other way. Right? And in the when you do that, what you typically get is some number of gapless Dirac fermions. Right? And that is the theory of U1 Dirac spin liquid here. And it turns out that the most relevant one is a theory with 4 Dirac fermions coupled to an emergent U1 gauge field. So 4 comes from the fact that I have 2 flavors for spin, that I have spin up, spin down, and then there's another 2 for valley that's required by fermion doubling. That's the minimum number I can have without breaking time reversal. Okay. Sorry. So for that, let me go back to the triangular lattice example. It turns out, which Juven actually mentioned, if I took the band structure I mentioned before, but turn off the spin orbit coupling, so I just have some pi flux around the lattice, that naturally realize 4 Dirac fermions, gapless. And I end up with this QED3 with NF equal to 4, which there are by now reasonable evidence from the numerical side that indicates that this might be a stable CFT. Okay? And so this theory comes with a pretty big a continuous symmetry group. So there's a SO6, which is basically the SU4 flavor rotation. I have 4 flavors of them. And then there's a U1 that corresponds to the conservation of the magnetic flux, for which the monopole is a charged operator. Okay? You can neglect the Z2, doesn't matter. What happens is that since this is, you can think of this at the band structure level as where different band topology meets at the same point. And naturally, you get several different types of monopole operators. It turns out the monopole operator in this theory forms a vector rep of this SO6. There are 6 different monopoles that are degenerate, have the same scaling dimension at the CFT level. So you view them as the most important primaries in your theory, basically. So it turns out if you go through the exercise I mentioned to you, but with some other types of mass, for example, that gives you other band topology, you get different symmetry breaking order. And they look like this. So some of them, as I already told you, look like 120 degree order. Okay? And the others look like this guy, which it's not magnetically ordered, so it has the full SO3 spin rotation symmetry, but it breaks lattice translation and rotation symmetries in this funny way. So it's a valence bond solid order with a 12-site enlarged unit cell. So the enlarged unit cell looks something like this. Okay. So this competition, the competition between these two funny orders was first discussed in this paper several years ago, actually also within the context here. Okay. All we do is we understand the monopoles, that they indeed behave this way. Okay. So that has two consequences. One is 2 minutes. Okay. Yeah. Okay. I think that's doable. So that has two consequences. One is that this symmetry breaking order, you expect them to be reasonably close to this algebraic or Dirac spin liquid. And the other thing is, within the Dirac spin liquid phase, you expect them to be important fluctuating degrees of freedom. They're basically primaries in the CFT. So they have some fingerprint in the in things like correlation functions or scatter. When you do scattering and so on, you can try to measure them. Well, they haven't been measured in real scattering thing, but they have been measured in a numerical experiment. So there has been a study on the triangle lattice J1, J2 spin half model that it's more or less known that it's a spin liquid. It wasn't clear what spin liquid it was, but then recently people numerically observed that there's a sizable weight, spectral weight around the K point in Brillouin zone, which looks like this kind of magnetic order, along with some other signature. But this K point amplitude is the fingerprint of the monopole from the Dirac spin liquid. Okay, so before I end, let me just briefly mention that you can try this game on any other lattice you like. Turns out on Kagame you have a very similar story, well, with a catch, which I won't mention unless you ask. But the thing is, if I try this on bipartite lattices, it turns out, well, I still get a competition between the familiar Néel and valence bond solid order, except within this Dirac spin liquid, there is a monopole, one of the 6 monopole, that transform trivially under all the symmetries. So it doesn't carry any non-trivial quantum number. So now it becomes an allowed provision in my theory. And from all the evidences, this provision is probably relevant. So most likely, this Dirac spin liquid phase is not going to be stable on bipartite lattices. There's a deeper reason why it's unstable. The trivial monopole always exists on bipartite. It has to do with a possible SU2 gauge structure, but I won't go into detail for that. So yeah, so that's my talk. So in summary, it's entertaining, at least for me, that band topology or even ancient concepts like one-near center or polarization actually plays a role in understanding quantum magnetism, even those exotic phases, and so thanks.
A couple of quick questions. So your duality dictionary didn't contain the case where the slave fermions go.
Sorry, can you?
Where the slave fermions go superconducting. That wasn't in your dictionary, but
That's not in my dictionary. That's a
maybe
Z2.
the better understood case.
That's better understood.
So there, basically, the end phase you get is topological. It's not symmetry breaking. Even if
Yeah.
the topological band structure, is
Yeah.
there a reason for the distinction between that and this case?
Sorry, say the last sentence.
Even if you make the slave fermions be topological superconductor, you
Yeah.
still get topological.
Yeah,
not a-
you get an SET. Yeah.
Not a symmetry breaking phase. Why is it different from here?
Well, then become toric core, right?
Yeah. It's different there, right? I mean, there you get an SET, right? The Vison may do funny things, but here you just get an ordinary symmetry breaking order.
I was just asking if there's a conceptual reason why
It's the Higgs phase.
Sorry. The conceptual reason is Z2 gauge field is stable. A Z2 gauge theory is stable in 2+1. U1 doesn't actually. There's no such a thing as U1 real topologically non-trivial U1 gauge theory in 2+1. It either becomes a free photon, which is equivalent to a superfluid, or confines, depending on whether you have monopole turns on or not. So the Z2 and U1 are very different in 2D. Yeah.
I guess I'm supposed to know the split. Are the statistics of the monopole always boson?
Yeah. Otherwise, you get some funny anomaly, I think.
There's no bad structure you can choose.
Well, you can. No, no, because it's supposed to be a local operator. So as long as you have a bosonic Hilbert space, you're not supposed to have that. That's actually a good anomaly detector.
At one point you added a spin-orbit coupling for your corner spin-orbit insulator.
Yeah.
But you have to go back and check that the quantity degree order is consistent with that term in the Hamiltonian or something. But normally it's not.
Sorry. So that
What's
term.
the logic of that?
That term breaks some of the original symmetries, keeps some of the other symmetries.
But that was by hand. You chose to break some symmetries there.
Yeah.
And then you have to make sure that the condensed monopole is consistent with what.
Yes, it's consistent. It's consistent in a trivial way because once you break those symmetries by this term explicitly, then it no longer makes sense to talk about the monopole property under those symmetries. Right.
Okay, but shouldn't one figure out the monopoles before you, or it doesn't make sense to even define them?
Oh no. The thing is, before you turn this term on, it's a Dirac fermion, so there are multiple monopoles. So the monopoles they transform as SO6, blah blah blah. What this term does is to break that symmetry, so you lift the monopole degeneracy and you choose.
Why am I allowed to do that?
No. That suppose you do that. There's nothing.
Okay, suppose.
No. I'm not saying energetically you're guaranteed to automatically have that. That's not clear, right? So this is from the Dirac spin liquid point of view. This is a way to probe, single out the monopole, right? You add the mass, you single out the monopole, then you study it. So you know which symmetry you've broken by adding that mass. So that process is controlled.
Maybe I could ask you, it's like having a vector or a parameter, you have three components, and you can choose any one or any combination to condense, but what he's doing is he's analyzing each component separately.
Yeah.
And then it's up to you which one you choose to condense.
Yeah. This is the simplest choice.
In this quantum spin hole in your
Yes.
field,
Yes.
the edge somehow you can gap out, or what was the?
No, the thing is, once the monopoles proliferate, you break the symmetries. So then the edge probably can be can be gapped out.
You can explicitly write down an edge mass term.
Well, the edge mass term couples with the monopole. Yeah. So once it's Higgs. Yeah.
Okay, let's thank Chong again.
All right.
Thank you.